Now we move to part 3. In this sharing, we will talk about the components of lithium-ion battery. We will talk about different examples of anode, cathode, electrolyte, and the separator. This is a subsection that we will cover today for the anode, cathode, electrolyte, and separator. Anodes of lithium-ion battery. Metal lithium. Metal lithium has a very high specific capacity as compared to graphite, which is about 10 times of graphite. The specific capacity is about 3,800. In addition, it has the lowest, or we say negative electrochemical potential. However, the application of metallic lithium will cause the formation of dendrite. In the first few cycles of charging and discharging, there could not be any problem. However, if you run the battery after several cycles and more, then the dendrite will form. The prototype of lithium-ion battery is lithium titanate disulfide, which made use of metallic lithium as the anode. The formation of dendrite material can cause internal short circuit. So the formation of dendrite can grow and eventually protrude the separator and cause the direct contact between the anode and cathode. You just imagine a strong oxidizing substance in contact with a strong reducing substance. What will happen? So there will be a very strong thermal runaway reaction, which may cause the lithium ion to catch fire. So, how to solve the problem? Scientists replace metal lithium with graphite, which is a intercalation or insertion material. Of course, because the sodium ion is bigger, you cannot use graphite to store the sodium ion in sodium ion battery. So why graphite? Because it is cheap and safe. Graphite consists of layer of graphenes, which can reversibly store lithium ion, and it has a very good electrical conductivity. By using graphite as the anode material of lithium-ion battery, we do not longer have dendrite formation. Of course, if you do not balance the capacity of the cathode with the anode, say we have a lot of cathode, excessive lithium ion can play out from the graphite. The graphite has already fully stored the lithium ion. However, there are still a lot of incoming lithium ion approaching the surface of graphite, and this will cause lithium plating, and the dendrite formation could form as well. Every 6 carbon can store 1 lithium ion battery, and we already go through the question with you in the part 2, how to calculate the specific capacity of graphite. Compare with metallic lithium. Graphite has a specific capacity lower than metallic lithium about 10 times. However, compared to the cathode of lithium-ion battery, the capacity of anode, for example, like graphite, is significantly higher than it. And then we come to lithium titanate, which is a long-living material. It can be cycled over several thousands and remain 80% of its original capacity. In part 2, we mentioned that an anode should have a lower reduction potential as possible. As such, the difference potential between the cathode and anode will be high and result in a higher cell voltage. However, lithium titanate has a relatively high reduction potential. It is 1.55 volt compared to the lithium metal. This results in a lower energy density as compared to the conventional lithium-ion battery, which is composed by lithium cobalt oxide and graphite. The significant advantage of lithium titanate is that it can be charged at a high rate as compared to conventional lithium-ion battery without causing the dendrite formation. To form the dendrite, lithium ion has to be reduced in the first place. When the lithium ion is reduced, it will be plated out as the lithium metals. Since lithium titanate has a higher reduction potential, the reduction of lithium ion is hindered, and hence the dendrite formation is hindered as well. And then we move to pure silicon or lithium silicon alloy. If you recall the previous slide, the specific capacity of graphite is 372 milliamp hours per gram. Here, the capacity of silicon can reach out 4,200. Two main disadvantages of using silicon as the anode of lithium-ion battery. The first one is the poor electrical conductivity, which will cause significant IR drop. And the second disadvantage of using silicon as the anode is the poor structural stability upon cycling. When lithium-ion intercalate into the silicon matrix, there are about 400% of expansion. And when lithium-ion deintercalate, or we say de-alloy from the silicon matrix, there are about another 400% of contraction. The cyclic expansion and contraction will cause the pulverization of silicon. Despite with these two significant disadvantages or challenges, scientists still want to do research on silicon because, as you can see over here, one silicon can accommodate 4.4 lithium ion. And compared to the graphite cases, 6 carbon atom can accommodate 1 lithium ion. Scientists try to engineer silicon nanowire instead of silicon film or silicon particle. This is because silicon nanowire can effectively relax the strain during the charging process. This can reduce the pulverization of silicon, and pulverization is very bad because it could mean the loss of electrical contact with the current collector. The loss of electrical contact with the current collector also means that the capacity fades away. And then we come to cathode. One important point I forgot to mention is that both anode and cathode should have good electrical conductivity and also good ionic conductivity. The former allow electron to transport easily and the latter allow the ions to transport easily. In cathodes, we have many lithium metal oxide, and this lithium metal oxide has relatively poor electrical conductivity as compared to the carbon-based anode. In this case is graphite. And hence in cathode, we need to add in some conductive agent, for example like carbon black. And this process will inevitable to sacrifice some energy density. As mentioned, the reduction potential of cathode material are more distinct from each other. We have the reduction potential of the cathode material ranging from 2 volts to 5 volts. The increase of reduction potential is due to the change of the bonding nature. Here we have a metal sulfur bond, metal sulfide bond. And then moving to high reduction potential, we have a metal oxygen bond, metal oxide bond. Here, the structures of cathode seems to be more complex than the anode. This is because we have a transition metal cation. The transition metal cation typically display 4 to 6 coordination with oxygen or with anionic cluster or ligands. So they form 3-dimensional open network structures. And that's one of the reasons why the capacity of cathode is smaller than the capacity of anode generally. The second reason is because transition metal elements usually will have a heavier, or we say higher, molecular weight. So this results in a lower specific capacity as compared to the anode. The capacity of the cathode material depends on the local charge neutrality. And due to the structure difference of the cathode material, lithium ion can transport in some crystal channels with a lower energy barrier. This results in 1D, 2D, and 3D ion transport material. Now, let's take a look at lithium cobalt oxide. The short form of lithium cobalt oxide is LCO. It is the first commercialized lithium-ion battery developed by Sony in 1991. The nominal voltage usually is given as 3.7 V. The theoretical cell voltage is 4.27. It can be used to power cell phone, camera, and laptop. However, it is relatively expensive due to the limited abundance of cobalt. And it is believed that cobalt is more toxic as compared to nickel and iron. Now, let's come to lithium iron phosphate. The short form of lithium iron phosphate is LFP. It is attracting to scientists because of the low cost as compared to lithium cobalt oxide. One important thing you must remember is that the LFP has a very good temperature tolerance. This material has a very good thermal stability and hence the safety concern is not a concern to us. The likelihood for LFP to suffer thermal runaway is lower than the lithium cobalt oxide. This is because the cobalt oxygen bond is weaker than the phosphorus oxygen bond. As a result, oxygen will be released from the lithium cobalt oxide more easily. In other words, the LFP is more resilient to oxygen loss. Hence, it is less susceptible to thermal runaway as compared to the lithium cobalt oxide. The LFP is commonly used in the EV, electric vehicles, because of the stable chemical and the thermal properties of the electrode. One interesting difference of the LFP as compared to the lithium cobalt oxide is that there is no lithium remain in the cathode when fully charged. This is not the case for lithium cobalt oxide. Approximately 50% of the lithium has to remain in the cathode when fully charged. However, the LFP suffer from relatively poor electrical conductivity. Conductive agents, for example like carbon black, can be used to improve the performance. Now, let's take a look at the structures of lithium iron phosphate. In this figure, lithium ion can only be transported in the 1D channels of the LFP. In case the structure is blocked by point defects or the structure collapse, the LFP will lose the capacity. Now, we come to lithium manganese oxide. Lithium manganese oxide has a spinel structures. The short form for lithium manganese oxide is LMO. It forms a three-dimensional network for lithium ion transport. In addition, it is referred as green because it is less toxic as compared to cobalt and it has a very good abundancy as compared to nickel and cobalt on the Earthcraft. You need to be reminded that the figure here is in the log scales. Hence, the abundancy difference between the manganese and cobalt and nickel are huge. However, the disadvantage of LMO is that LMO has less specific capacity as compared to the lithium cobalt oxide, and it is not suitable to operate at elevated temperature. We can change the property of LMO by doing some substitutional doping. Now, let's come to the NMC. N stands for nickel, M stands for manganese, and C stands for cobalt. The idea is that nickel has high energy density. However, it is not stable, and therefore we need to blend with cobalt. However, cobalt is expensive, and therefore we need to tune the ratios of these three elements. As such, the cost and the performance do not trade off very much. We can have different types of NMC based on the ratio between among X, Y, and Z. Structurally, it is resemble to lithium cobalt oxide. And therefore, you can think of this way to improve the conventional lithium cobalt oxide. In terms of the energy density, we can blend in nickel. And to improve the chemical stability at the interface between electrode and electrolyte, we can blend in manganese. You can see the characteristic of different elements in the NMC from this table. Now, let's compare the performance of different cathodes in lithium-ion batteries. First, we have a lithium cobalt oxide, which is proposed by Good Enough, and it is the first commercialized lithium-ion battery. And then we have LFP, which is the lithium iron phosphate. LFP is famous for the thermal stability and a good temperature tolerance due to the bonding nature of phosphorus and oxygen. And hence, the safety of LFP is improved and it can be used in an electric car. The next will be going LMO, lithium manganese oxide. LMO is developed because of the abundance of manganese is more than nickel and cobalt. However, it has a lower capacity as compared to the lithium cobalt oxide. We can further improve the performance of lithium cobalt oxide by blending in nickel and manganese. The nickel can increase the energy density and the manganese can improve the chemical stability. And that's all for the cathode part. Moving forward, we are going to discuss different types of electrolyte. In lithium-ion battery, aqueous electrolyte is not used, and only liquid, polymer, and ceramic electrolyte are used. The function of electrolyte is to provide ionic conductivity to lithium ions. However, it does not allow the transport of electron. Now, let's talk about the criteria, or you say the requirement of electrolyte. First, it should have a wide potential window. As such, the electrolyte will not be decomposed during the normal operation of lithium-ion battery. And then it should have a high ionic conductivity. In other words, the electrolyte should have a low viscosity. As such, the lithium ion can be transported easily. We don't want the electrolyte to be decomposed or degraded during the normal condition, and therefore it should have a good chemical and electrochemical stability. And ideally, an electrolyte should be able to work minus 30 degrees C to 60 degrees C without decomposition or without degradation. The fifth point is low volatility and low flammability. This is to prevent the battery from catching fire, which is thermal runaway. And then we have the last one, number 6, environmental friendliness. What you should bear in mind is that no single electrolyte can satisfy all the requirements listed here. In organic liquids electrolyte, often we will mix two of them together to achieve the desired performance or to achieve the desired characteristic. Now, let's look at the aqueous-based electrolyte. Aqueous-based electrolyte refer to the water-based electrolyte, and it is not used in the lithium-ion battery. The main reason is because of the electrochemical stability of water. From this figure, you can see that we have the anode material and cathode material of lithium-ion battery. And these are the CV curve, cyclic voltammogram, which is when the lithium intercalate and deintercalate from the electrode material. By taking the potential difference between the cathode and anode, we can get the cell potential. And the cell potential is larger than the potential window of water. In other words, the water will decompose if it is used as an electrolyte in the lithium-ion battery. So, the thermodynamic stability of water is 1.23 volts. However, kinetically speaking, usually the water can be splitted well above 1.23 volts. If we add some source into the water, for example like potassium hydroxide, KOH, the electrochemical stability of water can be improved up to 3 volts. However, in a normal operation, lithium-ion battery operate around 3.7 volts, and therefore water will be split undoubtedly. And if we split the water, it will generate hydrogen and oxygen, and these gases will pile up in the cell. Now, let's move to the organic liquid electrolyte, which is the most popular case in lithium-ion battery. Commercialized lithium-ion battery tend to use organic liquid electrolyte as the electrolyte. However, the disadvantages are that organic liquid electrolyte tends to be toxic and it is flammable. There's a risk that this electrolyte could leak out from the battery and will cause fire. To prepare the electrolyte, lithium salts is dissolved in the organic solvent. So here are the examples of lithium salts and organic solvent. We want the organic solvent to have a high ionic dissociation capabilities. An organic solvent that has a high dielectric constant, meaning to say that it can dissociate the lithium salts more easily, forming lithium ions. So as such, when we apply the current to the lithium-ion battery, the lithium which is the cation, and the anion can move opposite. We also want an organic electrolyte to have low viscosity. Low viscosity means the ion mobility is high. And therefore, organic electrolyte has two main purposes. One is to dissolve the lithium source, and the other is to allow the lithium source move easily. Last but not least, we also want the organic liquid electrolyte to have a high flash point so that it will not cause fire easily. An interesting question to ask is, why do we use LiPF6? Why don't we use LiCl, lithium chloride? Why don't we use LiBr, lithium bromide? Because the chloride ion can be oxidized and form chlorine gas on the cathode, and therefore we need to avoid using lithium chloride. So now let's take a look at the common recipe of organic electrolyte used in lithium-ion battery. We usually will blend EC and DMC together in 1:1 volumes. And then we will dissolve the LiPF6 to get the final electrolyte. Once again, I would like to emphasize that this is a very typical organic liquid electrolyte that you will see in many conventional lithium-ion battery. So the question is, why do we want to use EC? And why do we want to blend EC with the DMC? First of all, you need to remember that EC has a very high dielectric constant, meaning to say that it can dissociate lithium source effectively. However, looking at the melting point and the boiling point, EC has a high melting point and a boiling point, meaning to say that the viscosity is very high. At room temperature, the pure EC is a crystalline form, is in a crystalline form, and therefore we need to blend the EC with the DMC. The idea is that although EC can dissolve and dissociate the lithium source effectively, this source cannot move due to high viscosity. In other words, it has a very low ionic mobility. And therefore, we need to blend DMC to improve the ionic mobility. A final point I would like to touch on is some research say that only ethylene carbonate, the EC, can provide protective layer on the graphite and prevent further reaction, which we will talk about in the next slide, the SEI. Alright, SEI stands for Solid Electrolyte Interface. So it is formed at the electrode-electrolyte interface. The formation of SEI will consume the active material, for example like graphite, and the composition of SEIs are very complex. Now I want you to think in this way. SEI is a protective layer, as in the case of aluminum oxide on the aluminum foil. It actually inhibits further reactions of aluminum. So the SEI will inhibit the further reactions of the active material. So the SEI isolate electrode and electrolyte for further reaction, provided we have a very structurally stable SEI. So if the SEI is not mechanically stable and thermally stable, it will decompose and it will consume more and more the electrode material and consume lithium. So you will lose the capacity at the end of the day. The formation of SEI will reduce the maximum power density, especially if the SEI is not stable. It will form thick and it will form more and more thicker, and this will cause the battery to degrade. One of the reasons that the battery degrade over time is when we charge and discharge the battery, the lithium ion will intercalate and deintercalate from the SEI, and eventually the contraction and expansion of the SEI will cause the layer to crack and new SEI layer will form. Now let's move to the polymer electrolyte. As we mentioned that organic liquid electrolyte has a safety concern because it can cause fire. The solid, or we say gel-like, polymer electrolyte could possibly reduce the fire safety concern. In fact, the use of solid electrolyte could possibly remove, or we say eliminate, the use of separator. However, generally speaking, the solid or polymer electrolyte tends to have a lower ionic mobility. Here we have dry polymer electrolyte and gel polymer electrolyte. The dry polymer electrolyte is called POE. It forms a complex with the ion in a solid state. So usually, if the temperature increases to around 80 degrees C, the lithium ion can move more easily by assistance of the polymer change. And then we have gel-like polymer electrolyte, which is we put the polymer in a liquid electrolyte. So the liquid electrolyte are fully absorbed by the polymer matrix and it can avoid the leakage issue. So from this figure, you can see there are crystalline part, which is the polymer, and there are amorphous part, which is the liquid. As a result, the conductivity of gel polymer electrolyte is close to the conductivity of liquid, but higher than that of the dry polymer electrolyte. Last but not least, we have ceramic electrolyte. Ceramic electrolyte refer to inorganic solid-state material. They are ionically conductive. So this is different from a previous case where we have an organic material as an electrolyte. In this case, we have inorganic ceramic as the electrolyte. The ionic conductivity is very low at room temperature, and hence the ceramic electrolytes tend to use at the high temperature application. This type of electrolyte is proposed to be used for next generation electric car, mainly because of the excellent safety performance and that can enhance the customer confidence. Using the ceramic electrolyte, we can avoid leakage of the electrolyte and there is no fire hazards. In short, ceramic electrolyte are still in the research phase. This is because of the low ionic conductivity. The ionic conductivity mechanism are different from the one that in liquid phase. Now let's come to the last component of lithium-ion battery, which is a separator. The anode and cathode are separated physically by electrolyte salt separator to prevent internal short circuit. And in fact, a separator is required in many electrochemical systems with a liquid electrolyte, for example like fuel cell and capacitor. So these are the criteria for a separator. First, it should be electrical insulating to prevent electron flow. Second, it should be ionic conductive. Actually, separators are porous, as such the ion can flow through and migration. Third, it should be chemically inert, and when in contact with anode and cathode, there should not be any cell reaction. Last but not least, it should be mechanically robust to withstand tension or puncture by the dendrite, if any. Now, let's take a look at a separator made by PE and PP. A separator is a microporous polymer membrane, which is typically 25 micrometer with a porosity of about 40%. A separator should not be too thin, otherwise it will lose the mechanical support. A separator should not be too porous, otherwise it is not able to thermal shut down when there is a thermal runaway. So in this figure, we see a multi-layer composite made by PP, PE, and PP. The melting point of PE is 135 degrees C and the melting point of PP is 165 degrees C. In case of thermal runaway, the melting point of PE is low, hence it can shut down, the pore side will close. However, the PP can still serve as a mechanical support to separate the anode and cathode. So, in other words, we can say that the thermal shutdown temperature of commercial lithium-ion battery by using this kind of separator is about 135 degrees C. So it is like a thermal fuse. We have electrical fuse. When the electrical run in a short circuit, it will shut down. And then this one is like a thermal fuse. It will shut down the battery and the battery cannot be used anymore. However, it will not cause fire. So that's all for the components of lithium-ion battery. Let's come to the summary. We have covered different types of anodes and different types of cathodes. And we also cover different types of electrolyte. and briefly touch on the shutdown mechanism of separator. That's all for the part 3. Thank you.